So on to the inductor. The inductor on an AC supply behaves very differently to the resistor. We still have voltage, a current will flow, and the inductor will oppose the flow of current. Just to speak about that for a moment, an inductor will react against any incoming current. The current tries to enter the coil, it creates a magnetic field. The magnetic field induces an EMF in the coil that opposes the incoming current. So it has the effect of slowing down the inrush of the current. So if you just pause and think about that for a moment, the current is always going to have a delay. And we can draw that on this diagram here. So we still have the sine wave, which is our supply voltage, but the current is going to arrive later. It's going to reach its maximum 90 degrees later than the voltage. So the voltage is at its maximum there, and the current is going to reach its maximum later. So I can attempt to draw that in. So the current, oops. Okay. So not the prettiest, but it'll do. So the current is reaching its maximum 90 degrees later than the voltage. That's why it is really important to mark on the 90, 180, 270, 360 marks and get this drawing accurate. So there is the voltage at its maximum. 90 degrees later, the current is at its maximum. So the current has shifted along 90 degrees from how it behaved with the resistor. So this opposition to current flow, as I said, is called reactance. We'll deal with that again in just a moment or two. Firstly, let's look at this diagram. This is a waveform diagram, and we can make that look simpler by using a phasor diagram. So first of all, draw the voltage. There's the voltage. And then the current arrives 90 degrees later. So here is the current, and that angle between the two is 90 degrees. So this is the current through the inductor, IL. Just to finish this diagram, so we haven't got a load of arrows, this is a phasor diagram. That arrow rotates anti-clockwise, and there's omega to tell us angular rotation. Okay, so this opposition to current flow has a formula that goes with it. So we talk about inductive reactance. Inductive reactance, XL. This is reactance, and it's for the inductor. Inductive reactance is 2 pi FL. 2 times pi times the frequency times the value of the inductor in henries. And that's going to be measured in ohms. So instead of us having resistance as the opposition to current flow, we now have reactance as the opposition, still measured in ohms. Fortunately, Ohm's law still works. So Ohm's law, V equals I times R. But it's not R because we have an inductor, it's XL. I equals V over R. I equals V over R. It's not R. We replace R with XL. And the final formula, R equals V over I. It's not R, it's XL equals V over I. So this is still Ohm's law. We've just changed the letter. We've gone from R to X. Let's have a look at an example. Okay. So I've written down a simple example. A 100 millihenry inductor is connected to a 110 volt 50 Hz supply. Find 1. Inductive reactance, 2. The current taken. So this should be fairly straightforward. So part 1. XL is 2 pi FL. Put the numbers in. 2 times pi times the frequency. The frequency in the question is 50. The value of the inductor is 100 millihenries. Don't forget the milli. So 100 times 10 to the minus 3. And if you put that in your calculator, I'm hoping you'll come up with 31.4 ohms. So that's XL. The final bit is to find the current taken. So part 2. The current taken. Think of Ohm's law. I equals V over R. Well, it's not R, it's XL. Put your numbers in. The supply voltage was 110. XL we just found. And that comes to about 3.5.